It was never supposed to happen. In the late 1960s, Volkswagen engineers were certain they understood the Beetle's limits. Its tiny air-cooled engine was built for durability, not speed, and pushing it too far was considered reckless, even dangerous. Yet far from Wolfsburg and Detroit, a Mexican engineer quietly challenged that certainty. Using an approach many called impossible, and some called irresponsible, he forced the humble Beetle into territory reserved for muscle cars and exotics. The result shocked racers, embarrassed corporations, and rewrote what safe engineering meant, proving that some rules exist only until someone dares to break them forever, everywhere, quietly. The impossible physics of 1968. Picture this. It is 1968. The world is divided, not just by politics, but by the philosophy of speed. In Detroit, the big three are locked in the peak of the horsepower wars. It is an era of excess. Chrome, steel, and massive displacement rule the road. You have Chevy Camaros, Dodge Chargers, and Ford Mustangs rumbling down Woodward Avenue, their V8 engines gulping fuel and churning out 3, sometimes 400 horsepower without breaking a sweat. The formula for speed is simple. There is no replacement for displacement. Now, shift your focus south, about 2,000 miles, to the chaotic, vibrant streets of Mexico City. Here, the landscape sounds different. It doesn't rumble, it hums. The rhythm of the city is set by the distinctive air-cooled clatter of the Volkswagen Type 1, the car known affectionately as the Vocho. In 1968, Mexico was rapidly industrializing, and the Beetle is the backbone of that movement. It is the taxi, the family hauler, and the delivery van. But from a performance standpoint, it is a joke. In Wolfsburg, Germany, the engineers who designed this machine are very clear about its limitations. They view the Type 1 engine as a triumph of reliability, not performance. It is a masterpiece of minimalism, built around a magnesium alloy crankcase. That magnesium is light and strong, but it has a glass jaw. The prevailing engineering dogma states that if you push this case past a specific thermal and structural limit, roughly 60 to 70 horsepower per liter, it will fail. The metal will expand, the main bearing saddles will warp, and the engine will effectively dismantle itself from the inside out. According to the smartest people in the room, the absolute ceiling for this platform is maybe 100 horsepower. Anything beyond that is a ticking time bomb. So, you can imagine the confusion when a bright yellow Beetle rolls up to the staging lanes of a Mexico City drag strip in late 1968. It looks mostly like the thousands of other Vochos puttering around the Capitol. But when the light turns green, something impossible happens. It doesn't putter, it screams. This little yellow car launches hard, lifting its front wheels, and tears down the track, crossing the quarter-mile trap in 12.8 seconds at 108 miles per hour. To put that into perspective, a factory 1,500cc Beetle from that same year, with its 53 horsepower, would need about 22.5 seconds to cover that same distance. This car didn't just beat the factory standard, it effectively lapped it. But the real shock isn't the comparison to other Volkswagens. It is the comparison to the American giants. That 12.8-second run is faster than a 1968 Pontiac GTO. It is faster than a standard big block Camaro. A 4-cylinder, air-cooled economy car, utilizing technology that was supposed to melt at high speeds, is embarrassing the kings of Detroit on their own turf. This performance was not supposed to exist. By every metric available in the Volkswagen service manuals, that engine should have exploded halfway down the track. It was generating break-mean effective pressure figures that should have hammered the magnesium case into scrap metal. Yet, it held together. What the spectators were witnessing wasn't just a fast car. It was a forensic dismantling of a technical limitation that an entire industry had accepted as fact. Someone had looked at the rulebook written by Wolfsburg and thrown it out the window. That someone was Carlos Gonzalez, and he had just started a war with the laws of physics. The mechanic's forensic discovery. To understand how Gonzalez broke the record, you have to leave the drag strip and step into the workshop. Specifically, you need to look at what happens when a Volkswagen engine dies. Carlos Gonzalez wasn't just a tuner, he was a dealer-trained mechanic. He spent his days swimming in grease and magnesium dust, tearing down hundreds of engines that had reached the end of their service lives. Most mechanics look at a blown engine and see a pile of broken junk. They see a rod thrown through the block or a seized bearing and think about the replacement cost. Gonzalez looked at these carcasses and saw data. This is forensic engineering in its purest form. As he disassembled these motors, he started noticing a pattern in the architecture. The German engineers in Wolfsburg were famously conservative. They knew these cars would be driven in the freezing Alps, the scorching deserts of Africa, and the humid coasts of Mexico. They knew owners would skip oil changes and use low-grade fuel, so they overcompensated. They built a massive safety factor into the crankcase. Gonzalez realized that the magnesium walls of the engine block were significantly thicker than they needed to be for a 50-horsepower load. The main bearing saddles, the structural foundation that holds the crankshaft in place, were massive. It was like using a steel beam to hold up a picture frame. The structure wasn't weak, it was bored. But the real breakthrough came when he looked at the negative space. Inside the crankcase, around where the crankshaft spins, there were voids. Empty pockets of air that served no purpose other than clearance. He saw dead space. This observation changed everything. The prevailing theory was that the case was the limiting factor, that it couldn't physically contain a larger engine. Gonzalez realized the limit wasn't the box itself. It was the furniture Volkswagen had put inside it. The crankshaft was too small for the room. He hypothesized that if he could precision machine those internal clearance pockets just a fraction of an inch, he wouldn't compromise the structural integrity of those thick walls. Instead, he could fill that dead space with a rotating assembly that had a much larger throw. The 82mm secret. The heart of this mechanical revolution was a single heavy piece of metal, the crankshaft. In 1968, the standard Volkswagen engine used a crank with a 69mm stroke. In engine terms, the stroke is the distance the piston travels from the bottom of the cylinder to the top. It is simple mechanics. Think of the crankshaft like a wrench turning a bolt. The longer the wrench, the more leverage you have, and the more torque you can apply. Gonzalez didn't just want a little more leverage, he wanted a longer wrench entirely. He calculated that he could fit an 82mm stroke inside the case. That is a 13mm increase. In the world of precision engine building, adding 13mm to the rotating assembly of a compact block is like trying to fit a basketball into a golf hole. It requires a complete reimagining of the internal geometry. The problem was acquisition. Today, you can open a browser and order a stroker crank from a dozen different suppliers. In 1968, the global aftermarket for high-performance Volkswagens did not exist. You could not buy this part because, theoretically, it wasn't supposed to exist. So, Gonzalez improvised. He bypassed the automotive supply chain entirely and walked into a local machine shop in Mexico City that specialized in heavy agricultural machinery. This was a brilliant strategic move. Parts made for tractors and plows are subjected to immense stress and abuse. They require metallurgy that prioritizes absolute survival over cost-cutting. Together, they manufactured a custom crankshaft from a solid billet of high-grade steel. This was a quantum leap from the factory component. Volkswagen used cast iron or forged carbon steel, materials that are excellent for mass production and moderate power, but tend to shatter under extreme racing loads. Billet steel is grain-oriented and incredibly dense. It doesn't crack, it endures. The machining required surgical precision. The counterweights on the crankshaft, the heavy lobes that balance the engine, had to be completely redesigned. If they were too big, they would smash into the camshaft during rotation. If they were too small, the engine would vibrate itself to pieces at 7,000 RPM. Gonzalez and the machinists shaved and shaped the steel until it cleared the internal components by fractions of a millimeter. When this custom 82mm crank was paired with massive 94mm pistons, up from the stock 85.5, the math became terrifying for the competition. The engine displacement jumped from the factory 1,584 cc to a staggering 2,276 cc. This was often rounded up and marketed as the 2.3 liter. That is a 43% increase in displacement. Imagine taking a factory engine and instantly making it nearly half again as large, without changing the external footprint of the car. This wasn't just a modification, it was a transmutation. The engine that left that machine shop possessed a torque curve that looked nothing like a Volkswagen and everything like a tractor, pulling hard from idle all the way to the red line. The forbidden geometry worked, defeating the heat death. Making horsepower is actually the easy part of the equation. The real engineering challenge is keeping that power from destroying the machine that created it. In an internal combustion engine, only a fraction of the burning fuel becomes motion. The rest becomes heat. When you quadruple the horsepower, you are effectively quadrupling the thermal load placed on the engine block. This was the basis of the German engineers' fear. The Volkswagen crankcase is made of magnesium alloy. While magnesium is incredibly light, it has a critical weakness. It loses structural rigidity as it heats up. If the engine temperature spikes too high, the metal softens. Under the violent reciprocating forces of a 200 horsepower stroker engine, the main bearings would essentially hammer the soft magnesium until the saddles became egg-shaped. This phenomenon is known as case pounding, and it is usually a terminal diagnosis for the engine. Gonzalez understood that the factory cooling system was hopelessly inadequate for his goals. An air-cooled engine relies entirely on surface area to dissipate heat. The standard Volkswagen cylinders feature 24 cooling fins, which were perfectly adequate for shedding the heat generated by 50 horsepower. For his build, Gonzalez didn't just modify the existing parts, he machined entirely custom cylinders. His design featured 36 cooling fins, a 50% increase in fin count over the stock units. By cutting these fins deeper and stacking them tighter, he increased the total cooling surface area by approximately 40%. This meant the engine could shed heat significantly faster, keeping the cylinder heads from warping under the intense pressure of combustion. But air was only half the solution. In the Type 1 architecture, motor oil does double duty. It is a lubricant, but it is also a primary coolant for the internal components of the bottom end. Gonzalez treated the oil system with the same seriousness as a water cooling system in a race car. He installed high-flow oil pumps and plumbed in external oil coolers, ensuring that the lubricant remained within its optimal viscosity range. By attacking the thermal barrier from both the outside with air and the inside with oil, he proved that a magnesium engine could produce supercar power without suffering a catastrophic meltdown, breathing fire at 7,200 revolutions per minute. At this stage, Gonzalez had an engine that wouldn't explode and wouldn't melt, but he faced one final, invisible adversary: airflow. You see, an internal combustion engine is really just a glorified air pump. The more air you can move in and out, the more power you make. The problem with the stock Volkswagen cylinder heads was that they were designed for efficiency at low speeds. They had small, restrictive intake ports that worked fine for cruising around town, but choked the engine if you tried to push it past 4,500 revolutions per minute. It was the mechanical equivalent of trying to run a sprint while breathing through a coffee stirrer. To get the power he wanted, Gonzalez needed this engine to spin to 7,200 revolutions per minute. To achieve that, he had to fundamentally alter the fluid dynamics of the cylinder heads. He spent countless hours porting and polishing the intake and exhaust runners. This process involves grinding away the rough casting marks inside the metal to create a smooth, glass-like surface. The goal is laminar flow, ensuring the air moves in a straight, high-velocity stream without getting tripped up by turbulence. But smooth air wasn't enough. He needed more air. He installed significantly larger valves and engineered custom rocker arm assemblies. In a standard Beetle, the rocker arms, the little levers that push the valves open, have a very conservative ratio. Gonzalez changed the geometry to create massive valve lift, snapping the valves open wider and faster to gorge those thirsty 2,300 cc cylinders with air and fuel. The result was a transformative shift in the engine's character, best understood through sound. Everyone knows the sound of a standard Beetle, that friendly, rhythmic put-put whistle exhaust note. It is the sound of a low-stress engine doing low-stress work. When Gonzalez fired up the stroker, that sound was gone. At idle, it had a heavy, choppy lope. But at wide-open throttle, climbing past 6,000 revolutions per minute, it emitted a terrifying, high-pitched scream. This auditory violence was the sound of high brake mean effective pressure, or BMEP. In layman's terms, BMEP is a measure of how efficiently an engine can turn air into pressure on top of the piston. By combining the massive stroke, the porting, and the valve geometry, Gonzalez wasn't just burning gas. He was creating a pressure chamber that rivaled purebred race engines. The 800-mile test. Speed is impressive, but endurance is undeniable. While the time slip from the drag strip proved the engine was fast, the skeptics in the engineering community remained unconvinced. The prevailing theory was that the Gonzalez stroker was a grenade engine, a fragile, high-strung experiment that would detonate if subjected to sustained use. To silence the critics, Gonzalez decided to leave the safety of the quarter mile and hit the highway. He embarked on the Acapulco Run, a legendary 800-mile round trip from Mexico City to the Pacific coast. This route is a torture test for any cooling system. It begins in the thin, high-altitude air of the capital, climbs through steep mountain passes that place immense load on the drivetrain, and then descends into the suffocating, tropical heat of sea-level Acapulco. Unlike other Volkswagen publicity stunts of the era, such as the famous attempt to float a Beetle across Lake Chapala, which required extensive waterproofing and modification, this run required the car to operate as a standard vehicle. There were no support crews, no special seals, and no trickery. The result was a masterclass in reliability. The yellow Beetle tore up the mountain grades, passing struggling trucks and overheating sedans, and cruised through the coastal heat without the oil temperature gauge ever entering the danger zone. It returned to Mexico City with 0 mechanical failures. The corporate battle for control. As the legend of the Mexibug spread, it eventually reached the wrong ears. The Volkswagen legal department in Mexico City did not view Gonzalez's work as a tribute. They viewed it as unauthorized tampering with their intellectual property. They launched a lawsuit claiming patent infringement. The argument was that Gonzalez was modifying their proprietary technology in a way that could damage the brand's reputation for safety. But the courtroom became the setting for Gonzalez's most important technical demonstration. His defense was simple and devastatingly effective. He argued that he wasn't infringing on Volkswagen's patents because he wasn't actually using their engineering for the power-generating components. He presented the evidence. The billet crankshaft was his design and manufacture. The 36-fin cylinders were his custom casting. The cylinder head geometry was his own invention. He successfully argued that the Volkswagen crankcase was merely a passive foundation, a container. The engine inside that container was an entirely new architecture born from his own mind. The court agreed. Gonzalez won the case, and in doing so, he secured a victory far larger than himself. He established a critical precedent for the automotive aftermarket, that an engineer has the right to improve upon a mass-produced design, provided the innovation is truly their own. The corporation owned the badge on the hood, but Gonzalez proved he owned the mechanics under the deck lid, superchargers, and the open sky. If the naturally aspirated 203 horsepower engine was a violation of automotive norms, what happened next was a complete departure from sanity. By the mid-1970s, Carlos Gonzalez decided that his forbidden stroker engine had not yet reached its true ceiling. He looked at the 2.3-liter foundation he had built and asked a dangerous question. What happens if we force-feed it air? He sourced a massive supercharger, a blower, originally designed for a GMC diesel truck engine. This was a piece of industrial equipment meant to scavenge air for a massive commercial vehicle, and Gonzalez strapped it to the back of a Volkswagen Beetle. The result was violence. The supercharged Gonzalez engine produced a staggering 315 horsepower. To put that number in context, a 1975 Ferrari 308 GTB, the pinnacle of Italian performance at the time, produced about 240 horsepower. This humble Mexican Beetle was now significantly more powerful than the poster cars on teenagers' walls. On the track, it was recording 10-second quarter-mile times. In the 1970s, a 10-second car wasn't just fast. It was in the same rarefied air as purpose-built dragsters. It was a giant killer in the truest sense. But the most profound validation of this engineering didn't happen on the asphalt. It happened at 5,000 feet. The experimental aviation community is a group of people who are obsessively paranoid about mechanical failure, for good reason. If a car engine throws a rod on the highway, you coast to the shoulder and call a tow truck. If an airplane engine throws a rod, the consequences are often fatal. In aviation, reliability is not a luxury. It is a prerequisite for survival. Pilots began to take notice of the Gonzalez spec 2,300cc architecture. They saw the robust billet crank, the massive cooling capacity, and the smooth power delivery. And they realized this was an ideal power plant for home-built aircraft. Soon, these forbidden engines were being bolted to the firewalls of experimental planes. This was the ultimate mic drop in the argument against Wolfsburg. The German engineers had claimed the engine would melt if pushed beyond 50 horsepower. Yet, here were pilots betting their lives on these engines sustaining high RPM operation for hours at a time in the sky. The fact that the aviation community adopted the Gonzalez recipe proved that his modifications weren't just a party trick for the drag strip. They were sound, stable, and durable enough to fly. From outlaw to special advisor. By 1986, the automotive landscape had shifted beneath Volkswagen's feet. The cow look phenomenon had exploded out of Southern California and gone global, and at the center of this high-performance culture was the stroker engine. The specific geometry that Carlos Gonzalez had pioneered, the idea of putting a big crank in a small case, was no longer a secret. It was the industry standard for anyone who wanted a fast Beetle. Volkswagen found itself in a peculiar position. They could continue to ignore the reality of what their engines were capable of, or they could acknowledge the genius of the man who had embarrassed them. In a move that displayed rare corporate humility, they chose the latter. The company that had once unleashed its legal department on Gonzalez now offered him a job. He was hired as a special advisor to Volkswagen. This appointment remains one of the great ironies in automotive history. The very engineer who had been accused of creating dangerous, unauthorized modifications was invited into the inner sanctum of Wolfsburg to lecture factory engineers. He wasn't there to learn. He was there to teach. He showed them how the Type 1 architecture could handle stress loads they had previously deemed impossible. This partnership had tangible results. While the Beetle had long since vanished from American and European dealerships, it was still being produced in massive numbers in Puebla, Mexico. Gonzalez's insights into thermal management and component durability helped Volkswagen de Mexico refine the production of the air-cooled engine, keeping the Vocho alive and reliable well into the modern era. The outlaw mechanic had become the guardian of the factory's legacy, ensuring that the people's car could survive the demands of the 21st century. The open source revolution. In the end, Carlos Gonzalez gave the automotive world a gift far more valuable than a single fast car. When he cracked the code of the Volkswagen engine, he had every right to lock it down. He could have patented the 82mm crankshaft, sued imitators, and monopolized the technology. He didn't. He refused to patent the design. He understood that speed belongs to everyone. By leaving the design open, he allowed the aftermarket to flourish. Today, if you want to build a high-performance Beetle, you don't have to machine a billet of steel in a tractor factory. You can go online and order an 82mm stroker kit from a dozen different manufacturers. The forbidden geometry is now the global standard for air-cooled performance. This legacy speaks to the heart of Mexican ingenuity. It is a story about the periphery outperforming the center. In 1968, while the world watched Mexico for the Olympics, a mechanic in a local dealership was quietly rewriting the engineering textbooks of a German giant. He proved that innovation doesn't always come from a billion-dollar R&D lab. Sometimes, it comes from a guy with a dirty shop manual and a refusal to accept impossible as an answer. The experts in Wolfsburg looked at the magnesium case and saw a structural limit. Gonzalez looked at the same piece of metal and saw a challenge. His work serves as a permanent reminder to every mechanic, engineer, and tuner that the limits written in the service manual are not laws of nature. They are just suggestions, waiting for someone brave enough to prove them wrong.